This video is going to walk you through the next part of the notes, which is exponential models. So some real-life quantities increase or decrease by a fixed percent each year. It can be another time period. And the amount y of such a quantity after t years can be modeled by one of these following equations. Well, if you go to the next page in your notepad, at the top, you will see that there's two formulas. One is called the exponential growth model, and one is the exponential decay model. And notice that they're very, very similar with just basically one difference. Now, to go over what all of these variables stand for, A is the initial amount that you're starting with. Whether it's money and you're starting with $500 in your account, or if it's bacteria and you're starting with 2 bacteria, that's your initial amount. R is the percent increase or decrease, depending on the problem. Typically, you'll see that written as a decimal. It's not incorrect to write as a fraction, but normally it's more helpful to write it as a decimal. Now, I wanted to talk a minute about where the 1 comes from. 1 represents 100%. And no matter what A is or what it represents, we assume that what you start with is 100% of what you have. And then from that 100%, we're going to increase or decrease by this percent. It says the quantity 1 plus R is the growth factor, and 1 minus R is the decay factor. If you notice that your growth factor is greater than 1, that is an indication that it is growth. If that value is less than 1, then that indicates that it's a decay factor. So let's look at a few examples. This example says the value of a car, Y, in thousands of dollars can be approximated by the model Y equals 25 times 0.85 to the t power, where t is the number of years since the car was new. It says tell whether the model represents exponential growth or decay. Well, looking at this value in here, that either represents the growth factor or the decay factor, and since this is less than 1, that represents that this is exponential decay. Part B, identify the annual percent increase or decrease. Well, we just decided it would be a decrease since it's decay in the value of the car. How much will the car be worth in 4 years? Well, when it asks to identify the annual percent increase or decrease, in our case decrease, they want to know what is just the R value. So what we know is that 1 minus R, or our decay factor, is actually equal to 0.85. That means your R value is actually 0.15, because 1 minus 0.15 will give you 0.85. Now, to find out the value of the car after 4 years, basically all you have to do is plug in 4 for t, which is your exponent. So we are going to solve the problem 25 times 0.85 to the 4th power. And so that would be something, obviously, you'll need to use the calculator for, and the answer you get is 13.05. But remember, it said that the value was in thousands of dollars, so really the car will be worth $13,050. Now, if you look at part C, it says estimate when the value of the car will be $8,000. So what they're really saying is the answer is $8,000, but you have to decide after how many years. Well, there is a way to do this on the graphing calculator, and I will show you that in class, but really let's just think about it. Go back to the problem you just worked. When we had an exponent of 4, we found out the value at the end of year 4 was $13,050. So you know that it has to be after year 4. Well, just get your calculator and let's try to figure this out. If I use an exponent of 5, let's see what the price is at the end of year 5. You get $11,092 and some change. And what you need to remember is that the value you get, that's the value it was at the end of that year. So obviously it's not year 5. So let's go and try year 6. At the end of year 6, the value is $9,428 and some change. So still not $8,000. So let's try year 7. Oops. There we go. Now, at the end of year 7, the value is $8,014 and some change. It's really, really close, but it's not actually reaching, it didn't actually reach 8,000 by the end of year 7. However, when you change the exponent to an 8, the answer is $6,812 and some change. Now remember, that's what it was at the end of year 8. And what it was at the end of year 7 was 8,014. Even though it doesn't come out exact, what you do know is that at some point in year 8, it hit $8,000. Remember, this is what it was the end of year 8, but sometime in year 8, it hit $8,000. So you could say that T is approximately 8 years. Sometimes you have to do a little approximation to get, rather than get an exact answer, until we get a little farther in this chapter, and then we'll be able to get a little more of an exact answer. Let's look at one more example. It says in 2000, the world population was about 6.09 billion. During the next 13 years, the world population increased by about 1.18% each year. Part A asked you to write an exponential growth model giving the population Y in billions, T years after 2000. So let's start there and write the model. Well, to write the model, we first need our initial or our starting amount. Well, that was 6.09 billion. It told us this would be increasing, so that lets us know it is growth, and it's going to increase by 1.18%. You need to write that as a decimal, which will be 0.118. And then at this point, really just focusing on the model, your exponent would still stay a t. Now, again, the best way to write this is to actually go ahead and do this addition, and so the best model would be 1.0118 to the t power. Now we have a formula that we can use to answer the next part. It says estimate the world population in 2005. Well, basically what we would need to do now that we have a model is we are going to plug in a 5. When you get your calculator, 6.09 times 1.018 to the power of 5. That gives you a world population of about 6.46 billion. Again, part B, similar to part C in the previous example. It says estimate when the world population was 7 billion. Well, they're giving you an answer. They are really asking you to figure out the exponent. Now we know 5 is not big enough. You can try whatever you want to. Let's try, I don't think 6 is going to be big enough either. Let's try 7. When we put in 7 as our exponent, we get 6.6, so not quite big enough. So let's try 9. Still not big enough. Not growing very fast. So let's maybe skip ahead and do a larger exponent. How about an exponent of 12? There we go. Now remember, that's what it was at the end of year 12. So we better go back and just check year 11 just to make sure, but there's a good chance that it actually hit. Yep, and see the end of year 11 wasn't enough. So it's going to be the end of year 12, which would be 2012. So what I'd like you to look at tonight is I'd like you to look at, on page 300 and 301, I'd like you to look at problems 21 to 24 and then 29 to 32. And then tomorrow we will continue with exponentials models and look at a specific model that's called compound interest.